This is a brief look at the Gate Blade Optimizer playback feature of the index test box. First, let's document where the data to be analyzed is coming from. In 2004, HDC purchased an index test box from Actuation Test Equipment Company. The index test box was successfully demonstrated in March 2006, but instead of buying the proven instrument, the Hydra Design Center initiated a new project to make their own, just like it. Due to investigations resulting from many complaints to Department of Energy, Department of Defense, and Corps of Engineers Inspectors General, the Hydra Design Center changed the name of their project to Gate Blade Optimizer, or GBO, to get it off the IG's radar and hide what they were doing. In 2007, the Hydra Design Center field tested their Gate Blade Optimizer, an instrument that is a government-produced reproduction of the index test box that the government purchased from Actuation Test Equipment Company in 2004. In response to a FOIA request in 2009, the 2007 Gate Blade Optimizer field test data from McNary Dam was sent to Actuation Test Equipment Company in electronic format on a CD. The data was converted from GBO format to index test box format by simply changing the file name extension from .dat to .csv. This demonstration starts at the Visual Basic 6 programming environment to show how easy it is to go from writing and modifying software to running and testing it. F5 above the keyboard is the Run button used to launch the program. It's even better to use the full compile in the pull-down menu to get a deeper scan for syntax and linking of graphic items to their underlying code blocks. This is the main control bar that contains several pull-down menus. The leftmost pull-down is the main test selector menu. Click on the GBO data test function to start the analysis. The XY graph loads the most recent 3D cam profile data when it appears. The data panel has a Windows browsing tool to locate the GBO data files for analysis and display. On this computer, the data is stored in two folders identified as the 9th and 10th of August 2007. These are GBO data files that consist of 5,000 measurements taken at 1/2 second intervals. When you click on a file name, the GBO data feature loads, analyzes, and presents the data on 1, 2, or 3 monitors. Let's look at a few of the features and tools for analyzing Kaplan turbine data. Clicking on pause in the main toolbar will halt any of the turbine testing modes so data and programming can be observed and debugged statically. Clicking pause again will resume the playback. The strip chart shows selected data streams in the GBO data file, and the XY graph chart shows the blade to head and gate tracking behavior and corresponding flow, power, and efficiency. Clicking on the main toolbar hides it. Clicking in the upper left-hand corner of the graph will bring it back. Clicking the Show Utilities button at the left end of the toolbar calls the Data Analysis Setup menu. The industry-accepted method of displaying Kaplan turbine 3D cam blade to head and gate data puts the gate stroke along the x-axis across the bottom of the chart in percent and the blade axis up the left side of the chart in percent and degrees. The index test box graphing method adds flow, power, and efficiency as y-axis scales on the right side. These displays can be turned on and off at will. This list of heads shows value and color to identify the head levels that define this 3D cam. Clicking the Numbers On button displays and hides identifying values for the Kaplan 3D cam curves to identify which is which. This cam surface has 8 blade to head and gate profiles at 5-foot intervals. The heavy blue line is the best efficiency on-cam line for the existing head. To show how the best efficiency on-cam line behaves as head changes, the index test box has a simulator with a head ramper as a graphic tutorial aid. Head values can be simulated by entering them into the head button, moving the slider, or calling the ramper feature that automatically moves the slider up and down in 1/2 foot intervals. The gate simulator shows how the blades respond to gate position changes. The head value for the on-cam best efficiency profile comes from the gate blade optimizer data file being analyzed. As each data scan is read in, gross head is computed by subtracting tailwater from forebay, and if the difference between the input gross head and the plotted gross head exceed 1/10 of a foot, the graph is redrawn at the new existing head. A scaling tool makes it easier to evaluate what the data analysis is showing about the turbine. Clicking anywhere on the XY graph calls a point display to show the relevant values at the clicked-on point of the graph. Steady-state positioning accuracy and dynamic performance for hydroelectric turbine control systems are defined and quantified using methods and procedures prescribed by the American Society of Mechanical Engineers, or ASME, in PTC 29, and limits are established by the International Electrical and Electronic Engineers, or IEEE, in STD 125. Of interest from these are the measurement methods and limits for deadband and response time. The specified limit for deadband is 1%, or plus or minus 0.5%, and the response time is less than 0.2 seconds. The IEEE STD 1207 committee was formed to prepare a tutorial to assist purchasing agents in specifying hydroelectric turbine control equipment to make sure that what gets purchased will work properly. Let's look at a few features of the XY graphing program for Kaplan turbines and explain how the graph is formatted to display the data and how the limits are plotted over the data for comparison and evaluation. Click on the Show Limits button to display the limits utility. The ASME 0.5% button displays the industry standards from ASME and IEEE that are intended to accommodate the normal slop and hysteresis in the mechanical section of a turbine control system. The 3, 5, and 10% limits are for evaluating tracking errors during rapid slewing from one power level to another. These limits are expressed in percent blade error divided by percent of gate motion per second. Clicking on the degrees button calls the gate blade optimizer added deadband limits. These are at 0.3, 0.5, and 1 full degree. The first three were added by the Hydro Design Center to mask the inherent dynamic instability in their 3D cam and blade controller design. The 1 full degree limit was added by the Walla Walla district to make certain that the instabilities were completely masked in order to avoid over-exercising the turbine blades and prevent premature trunnion bearing wear. Compliance with the 1% deadband industry standard is accomplished by every single private sector turbine control system vendor, and typically by an order of magnitude or more. The purpose of this video is to show just how poorly the government designed and produced equipment performs. One must wonder why. Instead of buying proven, accurate, competitively priced turbine controlling equipment from competent, legitimate suppliers in the private sector, these government engineers are designing their own equipment. This government-designed equipment is then given to a captive supplier, Automated Control Systems Incorporated, or ACSI, which is a company created by the government to mass produce and deploy this equipment throughout the Corps' Columbia River plants. When this dubious engineering and manufacturing arrangement and the resulting substandard blade positioning accuracy were brought to the attention of Corps of Engineers Inspector General, the response from Hydro Design Center was, "We know about it, and it's close enough for our purposes." When the industry standards were cited to provide a comparison to show just how bad this was, the Hydro Design Center replied that the blanket contract that they have with their captive supplier does not mention the industry standards, so they do not apply and have been waived. When the Inspector General was advised that there was a 12-plus year-long lawsuit involving these machines, and that the judge had ordered that only the best available science could be used in any of the hydropower facilities on the Columbia River per the Endangered Species Act, Corps of Engineers Inspector General broke off the conversation, telling me that I was a nuisance and a troublemaker.